What's going on, everybody? This is it. This is the moment you've been waiting for. No, not because this is the second last lecture of the entire semester, but because we are now ready to talk about how to use the so-called root locus and turn that into a design tool in order to allow us to design not only PED controllers, but also more advanced linear controllers or compensators, such as our phase lead and phase lag compensators, okay? So essentially what we want to do here to put us into the right mindset is that we have our open loop transfer function. It could be just the plant itself, the plant in some nominal controller you have designed. And then you say, boy, the closed loop pole locations in terms of how they move in the root locus, they don't really go through exactly where I'd like to have my poles in the closed loop fashion. So the idea here is to come back and say, okay, not a problem. I'm just going to throw another controller in front of everything, or a compensator that will add poles and or zeros to the system. And by adding those additional poles and or zeros, I'm going to modify the existing root locus and bend the branches to one side or onto the other side, and modify the location of the closed loop pole along the new branches. Okay? And that is the idea here. But before we can even think about doing that, we need to step back a second and think about what would be the effect, now that we know how to construct a root locus, what would be the effect of adding a pole? How would that affect stability? How would that bend the branches? How would that affect the number of asymptotes? And similarly, we're going to do the same thought process about adding zeros to the root locus, okay? So let's first talk about adding poles to the root locus. What would it do to an existing root locus? Because remember our quick example we had done for the PD, modified PD controller applied to spacecraft rotational single axis control. We ended up with this very simplistic root locus and looked like that. And that was in a closed loop fashion, right? This is controlled by the modified PD controller. Where you say, gee, you know what? I'd really like to have my poles here and there so that they satisfy the specs I have on TS, on maximum overshoot, or rise time, and so on and so on. So these pole locations would be ideal for me, yet I know that if I have this root locus, I'm kind of constrained to move my closed loop poles along the two branches like that. And no matter how I crank the gain of my open loop transfer function, I'll never be able to move my poles away from their respective paths and end up there. So the solution will be to come in and add additional poles and zeros to band the branches of my root locus to make sure that they now go through the exact location I'd like them to be at in terms of the pole locations. And then we're going to figure out the gain, and we'll ensure that those poles end up exactly there along the new branches. So this is the idea. But what would be the effect to an existing root locus of just adding poles? Okay? So if you think about it, if you add a pole, it will increase the number of asymptotes, correct? Because the number of asymptotes is related to n minus m. So if you add one pole, n minus m will go up by 1. Okay? And furthermore, if you look at the orientation of the asymptotes, measured counterclockwise positive from the real axis, we're going to lower the angle of the first asymptote. Right? Again, going back to the quick sketch we had, real, imaginary, 1, 2. So 2 poles, 2 asymptotes. Now, if I were to throw a third pole here, you know that we end up with 3 asymptotes. So instead of being at pi over 2 and 3 pi over 2 in terms of angle, Well, the first asymptote, that one, will end up at an angle of 60 degrees. So 60 degrees compared to 90 degrees originally, we have effectively lowered the angle of our first asymptote. First asymptote was shooting straight up. We've added a third pole. Now we end up with 3 asymptotes, 1, 2, 3, and the first one is at the lower angle. The effect of this is that it is going to push the root locus to which direction originally, and then one more pole, boom, we're going to the right. Push the root locus to the right. This is the effect of just one extra pole inside a root locus. As a result, as you move further to the right in the complex plane, it means that you're going to increase your settling time TS. And because you're moving more to the right towards the unstable region, ultimately it means also that you're becoming less stable or closer to instability. Now, is that a good thing? I'd say no. Sad face. Okay? This isn't too neat. But the location of this added pole within a complex plane on an existing root locus will also have an impact. Not all added poles are equal in terms of contribution to an existing root locus. Okay? Some poles will have a great effect and some poles will have a negligible effect. So let's talk about the location of the pole. So as the pole, I'm always talking about the added pole, obviously. So as this pole moves further to the right, the impact is that the center of asymptotes, or the intersection of our asymptotes with the real axis, same thing, is going to shift to the right. This is my sigma. Okay? So not only do I create branches that are banded at the lower angle towards the right, but also the intersection of all my asymptotes is moved further to the right. So I'm just making things even worse. I'm going to say further aggravates. Just say the push to the right. And that's not a good news. Okay? Let's go back for a quick example. Real, imaginary. Now let's say this, up, and then down, like that. So if the added pole is kind of further away like this, and that one's going to shoot straight to the left, that one straight up, and that one straight down, okay? As this added pole is being added closer and closer and closer to the original two-pole system, the complex plane, that would push this intersection further and further and further to the right. So if this one is really close here, that intersection of the two asymptotes, or now the three asymptotes, is going to be, or the breakaway point essentially, is going to be closer and closer to the instability region. And that would look something like that. Okay? So now a tiny little gain of the open loop transfer function could push everything to become unstable. Not the best situation. Okay? So that is the net effect of adding a pole in terms of the behavior of an existing root locus. Okay? It just makes things less stable because we're pushing things to the right by shifting the intersection of our asymptotes with the real axis to the right. And also, we're bending the branches or the asymptotes further down and making things easier to fly off to the right. But what about adding zeros to our root locus? Well, it is going to be the other way around, because if you add a 0, n increases by 1 or 2, if you add 2 zeros. So it's going to lower n minus m, therefore reducing the number of asymptotes. How is that even possible? Well, that makes sense, because if you add an extra 0 to the root locus, that 0 will be able to act as a receptacle from one of the poles that would otherwise fly off to infinity along an asymptote. Now that pole that was originally flying off is now being catched, or is now being caught by this additional 0. Okay? So that is a great thing. So lower the number of asymptotes, or in other words, catching a pole that would otherwise fly off to infinity along an asymptote. Additionally, we are going to increase the angle of our first asymptote. So instead of being 60, 180, and 300 degrees, now we went from 3 to 2 asymptotes, and all of a sudden the first one, instead of being at 60 degrees, ended up at 90 degrees. So we're increasing the angle of our first asymptote. And that is fantastic. We like it, okay? Because that means that we are pushing, okay, our root locus now towards the left. And left is pretty good when you talk about a complex plane. And as a result, we're going to lower the stabilization time and overall just make things more stable. The location of this added 0 also has an impact, okay? Because not all 0 we're going to throw to the complex plane will have the same effect on a root locus. So as the added 0 moves further to the right along the real axis in that direction, we are going to move the center of asymptotes towards the left. Thereby further improving performance of the closed-loop system and stability. And that is a very good news. Okay? Now that we understand the effect of adding 0 in terms of bending the branches of our root locus and adding a pole in terms of pushing things further to the right and stuff like that, we are now ready to look at advanced controllers, advanced linear controllers. Okay? Because we won't be restricting ourselves to P and PD, but we're going to look at new controllers, so advanced linear, I'm going to call them compensator. Okay? Because again, the difference between a compensator and a controller, and I've talked about it at least 2 times already, is that a compensator not only will be able to bring the tracking error down to 0, but will have an additional beneficial effect, and that will be to add some filtering action to the closed loop system. So whenever you have noise, which is kind of inherent to any practical applications, using a compensator will have some benefits for you. Okay? However, the price to pay is a slightly more complex structure in terms of transfer function compared to that of a simple P or PD controller. Okay? So the first one of which, in terms of advanced compensators, is going to be the lead compensator. Okay? So the transfer function of this particular compensator is going to be K, its gain. Think of it as equivalent to KP or KD for our modified PD controller. Okay, but because a compensator only has one gain, just denoting it with K is sufficient, times S plus 1 over T over S plus 1 over alpha T. And that is for alpha between 0 and 1. So what it does is it adds one pole located at S equal minus 1 over alpha T, and it adds 1, 0 located at S equal minus 1 over T. I'm going to say this compensator adds 1, 0, and one pole to the complex plane. However, doing so will not change n minus m, okay? Because we are increasing n by 1, but m gets also increased by 1. So the net n minus m number of asymptotes doesn't change. Okay, so the number n minus m of asymptotes doesn't change because 1, 0, and 1 pole doesn't change the factor n minus m, obviously. Now, because alpha is always between 0 and 1, it means that you have your pole always to the left of the 0. So this is the net contribution to a root locus of a lead compensator. It adds 1, 0 and 1 pole, always organized in this fashion. Always the 0 will be further right and the pole further left, like that. Now, they could be closer together or further apart. We don't care about that. That's going to be a design decision. But the fact that the pole is always to the left has to be like that, okay? So because the 0 is going to be closer to what's happening in the in terms of the original pole locations that are somewhere here probably, it will mean that the 0 will have a greater impact overall than the pole. And that's a great thing because we know that the 0 tends to pull the root locus to the left and make things more stable, okay? And this is why we need to have the 0 to the right of the pole, because the 0 organized in this fashion will always have a greater impact on the overall root locus. Okay? I'm going to say it is going to shift the root locus to the left, or help in terms of stability. Doing so implies that we're going to modify, obviously, our transient performance. Hopefully to the better. If you do the design right, you're going to improve the transient performance in terms of stabilization time, for example. Because you're going to pull everything further to the left, and the more you move in that direction, the lower stabilization time becomes. Okay, or the closed-loop system will respond faster to a given command. Instead of converging in 10 minutes, you might be able to converge within 4 minutes to the desired command, okay? So stabilization time will be improved. Okay, so these two effects are good things. Boom, boom. Okay? Now, I'm not going to go into the details yet about how we locate the zero and the pole of this lead compensator and how we're going to calculate the gain. I'm going to save that for after the discussion about phase lead, phase lag, P, and I think I'm going to talk about the PI as well. Okay? But I'm going to give you 2 examples in the next lecture. And through those examples, we're going to go step by step about how to design a lead and a lag compensator. But I didn't want to give you just the methodology in terms of theory. And then in the next lecture, the numerical examples. I'd rather have those 2 hand in hand to really improve the understanding on how things work here. Okay? So next lecture, we're going to look over the steps or the methodology involved in designing a lead and a lag. And we're going to do that with actual numbers to better illustrate how things work. Okay? It's going to be easier for you to grab onto this new theory. So this is the lead compensator. Adds 1 pole, 1 0. The pole is always further to the left to make sure that we pull our root locus further to the left and thereby improve the transient performance. For those of you who are already familiar with lead lag compensators, the calculation of the respective location for the zero and the pole of that specific compensator will be done through the phase condition, and the calculation of its gain, K, will be done through the magnitude condition. So those 2 conditions will ensure that we bend our root locus exactly in a way to make sure that it passes through the desired pole location. And the magnitude condition will ensure that we're going to stop the poles exactly at the right bus stop along the new paths we have defined to ultimately obtain the desired pole locations in a complex plane. All right. Let's talk about the other compensator known as the lag compensator, for which the transfer function is going to be defined as a gain, K, times S plus 1 over T over S plus 1 over beta T, like that. And that is for beta larger than 1. And this one is going to surprise you, K will be approximately equal to 1. All right. So what it's going to do is that we're going to add, similarly than before, 1 extra pole and 1 extra 0 to the complex plane. And exactly as per before, the fact that we're adding 1 pole and 1 0 will not change the number of asymptotes quantified by n minus m asymptotes. And also, if you look at the respective position of the pole and the 0 for this compensator, we are going to get the 0 almost on top of the pole, yet slightly to the left of the pole, like that. Okay? So because the pole now is further to the right, it will have a greater impact on the overall root locus, and therefore that means that this will slightly push the root locus further to the right. Oh, this is scary a little bit, isn't it? Yes, but those 2 elements are almost on top of each other and thereby almost canceling the respective effect. So you say, well, then what's the point? First off, we're making things a little bit worse in terms of stability. And second, you're saying that the respective contributions is always nullified. So why would you want to do that, especially if the gain is almost equal to 1? Well, the point is that this specific compensator is used not to modify the transient performance. Okay? I'm going to say almost no effect on the transient performance. Okay. Then, if we're not improving or making things worse in terms of transient performance, why would you need that? Well, the reason is to improve the steady state performance. And that is a great thing, okay? The fact that we're not modifying the transient is kind of neutral. It's like, yeah, okay. And what's the point? Well, the point is that this specific compensator is used whenever you need to improve the steady state performance. All right? So that would be similar to a proportional integral controller where you add an integrator at the origin to improve the type of the system to make sure that you reduce the steady state tracking error. Okay? So this is very similar to a lag compensator. So based on the situation you have to deal with, are you trying to improve the transient performance or the steady state performance? You're going to pick either a lead or a lag compensator respectively. Lead to improve the transient and lag to improve the steady state performance. If you need to improve both, well, feel free to cascade a lead with the lag compensators back to back in the open loop direct path. But that will work fantastically, okay? One thing that I want to give you a heads up on is that although those two things are almost on top of each other, they're still separated by a factor beta. Okay, notice the difference here. The 0 will be located at minus 1 over t, as the pole will be located at minus 1 over t divided by beta. So the pole is always closer to the imaginary axis for that reason, as shown here, and quantified by the 1 over beta t term. But because we're going to set this pole so close to the imaginary axis, and that will allow us to put the 0 beta times further to the left, yet because x is going to be so close again, 5 times or 6 times this very small distance will end up with a 0 location here. So in the grand scheme of things, when you have things all the way up there, yes, this is almost negligible because from that great perspective or point of view, those two are practically on top of each other. But if you come in and zoom here, you would see that the 0 is beta times further to the left than the pole, okay? But if you move your magnifier, you could pretend that they're on top of each other and thereby not moving the transient performance at all. All right. And again, we'll look at how to practically design a lag compensator in the next lecture as we go through a specific example. Now, one thing I wanted to do here is go back to a PD controller. Although we've used plenty of times a PD controller in this course, I still want to go back to it and make the connection between a PD controller and a lead compensator so that we better tie all things together. Okay? So PD controller, obviously quantified through its transfer function as Kp times the error, just the transfer function, okay, Kp plus Kds, or alternatively, this could be written as being Kp being factored out, so 1 plus Kd Kps, that. Or, according to many textbooks, I'm going to write it as being 1 plus what's known as TD times S, where obviously TD had been set equal by definition to KD, KP like that. Or if I want the S term on its own, I'm going to say that this is equal to KP that multiply S plus 1 over TD, like that. So what do we do here? Are we adding a pole? Are we adding 0? Are we adding both? Well, look at what we have in terms of the transfer function. There is no denominator. So all we're doing with a PD controller is to add 1, 0. And that's it. Meaning that, as per our previous discussion, we're going to lower the number of asymptotes. We're going to increase the angle of the first asymptote. I'm just copying what we had established in the beginning of this, okay? We are also then pulling the root locus to the left, which is a fantastic idea. And thereby, we are lowering stabilization time and making things more stable as a whole. Okay? So if you remember our discussion on lead compensator, it was a similar idea in terms of net effect, right? The lead compensator's objective was to make things more stable and particularly to improve the transient performance, exactly as a PD controller. So if you compare a lead defined by its 0 and pole here, this is lead in black, to a PD controller which only adds a 0, then you could say that a PD is a limit case of a lead whenever the pole of the lead is flown out all the way to minus infinity along the real axis, okay? So PD is a limit case of lead in which the pole is at minus infinity. So this is the kind of relationship we have between a PD and a lead. They're both used for the same purpose, to make things more stable, and a PD is actually a lead for which the pole was decided to be set at minus infinity. Think of it this way, okay? Good. Now, what about the analogy between a lag compensator and a controller? Yeah, that'd be a good idea. So let's do that. We're going to compare our lag controller, whose objective is to modify or to improve the steady state performance, to a controller designed specifically for the same purpose, and that one is a PI controller, proportional integral controller, for which the transfer function is going to be Kp plus Ki over S. Okay. And to better understand where I'm adding a pole and or a 0, I'm going to rewrite this slightly differently. So I'm going to factor out the Kp term and end up with 1 plus Ki over Kp S like this. Okay, or I can rewrite that as Kp times 1 plus 1 over Tis, or obviously Ti had been set to be equal by definition to Kp over Ki. And then I'm going to put everything onto the same denominator here inside the brackets to rewrite Kp Ti plus 1 over Tis Tis on top too. That was just 1. So it needs to be Ti times S plus 1 like that. And then I'm going to make sure that I end up with S plus something for the numerator so that I can rewrite it as being Kp S plus 1 over Ti over S, right? So if I divide the top with Ti, I get S plus 1 over Ti. But if I divide the bottom with Ti as well, I just get S, and the two Ti's cancel out, or so, okay? So all this to say that here, I can now clearly see what does a Pi contribute in terms, of pole and zeros. Because a Pi adds 1 0, located at S equal minus 1 over Ti, but also one pole, where? Well, at the origin. So you can clearly see that the pole is further to the right than the 0. So if you were to compare a Pi with our previously defined lag compensator, you would see that a lag has the pole and the 0 close to each other and very close to the imaginary axis. And that a Pi, so this is lag, and a Pi would be very similar, but with the pole directly at the origin and the 0 to its left, like that. Pi. So what does that mean? Well, it means that a Pi is actually a limit case of a lag in which the pole is at the origin. Okay? And lag was used whenever we were aiming to improve the steady state performance. And just by looking at it, you can say that a Pi has the same objective, because a Pi adds one integrator to the open loop transfer function and thereby increases the type of the open loop transfer function by 1. And if you remember, increasing the type means that you have an easier time to track more and more challenging reference signals in steady state, okay? So again, those two are related. So Pi being a limit case of a lag, and a PD being a limit case of the lead compensator. That is for today. That's all I had to say for this one. Keeping the more bulkier lecture, in which we're going to go over 2 complete examples in terms of designing a lead and a lag compensators. I'm saving that for next time. Okay? That's it. Until then, keep up the good work as usual. See you next time.